So this is part 284C3M1B7C8E13C9C6D3P38D19D7b37. And it's line 22f1fa19C3M1B7C8E13C9C6D3P38D19D7b37 mid-infrared optical frequency combs, 5G Wow Seti. And there's our alien radio signal. And there's our data there. Back good. Okay, so I had to keep the data together, so it's probably going to be another long one. This is a single crystal ultraviolet grade MGF2 resonators optical frequency PDF results and keyword research from the WOW data. Okay, so on May 4th I was working on this. Today's May 19th, 2013. So the data continues from a previous line of video, high Q crystalline microresonator signals. The keyword is Fonnula particles, wavelength formulas, and Compton wavelength. And then I found Fonnula units, time mole 1472. And I googled it and I got all these PDF results. So the quote PDF results are from a blog, mid-infrared optical frequency combs at 2.5 ohm based on crystalline microresonators. And okay, so this is the same PDF, but then I divided it up. Okay. We just looked at it in the previous video, and this one has pictures, so I guess I pulled up the pictures. Properties of an MGF2 crystalline WGM microresonator. So 17 ohm, and then diameter is 700 ohm. And then it shows FSR, GHZ, anomalous, GGD, and then some calculation there. D2 2 pi MHZs, wavelength ohm. So A is a finite element simulation of the optical intensity profile of the fundamental WGM at wavelengths of 2.45. I'm going to say because it just looks like that to me. Superimposed on a scanning electron microscope image of a 700 ohm diameter resonator used in this work, fabricated by polishing and shaping an ultraviolet-grade MGF2 cylinder blank. Absolutely no idea what that is. So the scale bar of 10 ohm, the radius of curvature of the resonator protrusion, which confines the WGM in the azimuthal direction, is 17 ohm. I don't know if that's how you say azimuthal, but I'm just guessing. Okay. So B is optical microscope image of the resonator, and C is the figure shows the simulated FSR for fundamental modes with mode number M, and then there's a calculation there. Mentions a blue curve, and the difference of FSR between adjacent modes is another calculation, and this is a red curve. As a function of the wavelength for the resonator in panel A, exhibiting an anomalous GBD, and then there's another calculation there. To fabricate the resonators, single crystal ultraviolet grade MGF2 was first cut into cylinder blanks with dimensions of several millimeters. Resonators were then shaped and polished on an air-bearing spindle by diamond abrasives to achieve a smooth protrusion, which provides an azimuthal WGM confinement, following the methods described in detail in reference 33. And of course, you'll have to go to their website to see that reference, because I'm not going to copy and paste every single thing that they say. What I basically do is look for whatever notes that talk about signals and stuff, and then I put them here so I can keep the data together, and then I give credit to whoever made it. And I'm basically just studying their work, and I'm video blogging what they do. Okay, so a scanning electron microscope was used to measure the transverse radius of curvature of the resonator of 17 ohm, figure 1a. The resulting mode area of the WGM was determined in a fully vectorial finite element simulation. Superimposed on figure 1a is the intensity profile of the fundamental mode at calculation there. From these simulations, we obtain an effective mode area, and then there's a calculation again, and with an AEFF to it. and determine the effective nonlinearity of the resonator, and it's a YEFF, and then there's a big long calculation there, and it says Caroline nonlinearity, and then another calculation. So the diameters of the resonators typically range from 500 ohm to 5 mm, corresponding to a resonator mode spacing in the range of 10 to 110 gigahertz. Tapered optical fibers made of silica were used for characterization of the resonators at 1.55 ohm. For pre-characterization, the quality factor of the resonances was measured with a tunable narrow line width, short term less than 100 kilohertz, fiber laser at at another calculation, yielding intrinsic Q factors exceeding 10 to the power 9, corresponding to a typical finesse of F equals 10 to the power 5 minus 10 to the power 6. Additional, no, it's not minus, maybe it's 10 to the power 5 to 10 to the power 6. I think that's what it means. Additional iterative thermal annealing and polishing steps may further increase the Q factors. Generation of mid-infrared frequency comb. We pump the resonators by a continuous wave CW mid-infrared laser based on an optical parametric oscillator that is tunable between 2.4 and 2.5 ohm with short-term line width less than 100 kHz. Details of the laser source and the experimental setup can be found in the methods section in Figure A2A. Optical power levels of 200 MW to 1 W were coupled into the resonators by employing a tapered fiber made of low OH fused silica. So silica comes up again. Then there's another calculation. And the resonator and tapered fiber are embedded in a dry nitrogen purged environment as water vapor is highly absorptive. So it's got the keywords. Oh, I better write that down. Oh, I didn't see that. It's got a bit of a formula here. Interesting. So we've got silica, we got vapor, and we got water being mentioned. So this could go with that invention that came up earlier. So it uses a resonator. Tapered fiber are embedded in the dry nitrogen purged environment as water vapor is highly absorptive. In the mid-infrared, prior exposure to air, however, is not expected to lead to accumulation of water layers of MgF2 crystals are hydrophobic. So again, we've got some hydrophobic crystals, which is what we're using to create a signal with. So I'm going to make a note of that. I'll add these in the tags, I guess. The output spectra were recorded by an optical spectrum analyzer with cutoff wavelength, with cutoff wavelength at 2.5 ohm. Figure 2b shows the optical frequency comb spectrum derived from the 700 ohm diameter resonator pumped with squiggly line 600 MW of laser power at, again, there's a calculation there. We observed more than 100 modes spaced by 107 GHz, corresponding to a span of over 200 nm, which corresponds to the FSR of the resonator. Get another calculation, where R is the cavity radius and C is the speed of light in vacuum, and Nef is the effective refractive index. So you want to use those calculations with your when you do this. We've got speed of light coming up, Nef. So we have effective refractive index. So I'm going to do effective refractive index. Good thing I leave some space in between the videos. I write them down on my notebook here. See, I'll show you. I write everything down on my notebook, and then I put check marks when I do stuff, because if I didn't, I would never remember I did it. Fun, isn't it? Okay, so where was I? I have no idea. Oh, refract. Okay, the resonator has a high optical finesse. So F equals 1.2 times 10 to the power 5. Optical sidebands can be generated. Once the parametric threshold is exceeded. I'm sorry, I should have wrote up a formula for this. This is so good. So the threshold for parametric oscillation can be estimated as the point where the Kerr nonlinearity, again nonlinearity is a huge word and so is Kerr, induced frequency shift, we've seen that before. Then it's got this little symbol with Kerr, reaches half the cavity decay rate, the bistability point, that is as, and then there's a long equation there, where n is the refractive index, n2 the Kerr nonlinearity, p is the coupled power, or p coupled, the power coupled into the resonator, AEFF the effective modal area, F the cavity finesse, and K the cavity decay rate, and W the optical angular frequency. This is weird because when I just did like a formula in another video, I mentioned these different letters doing different things, and it's strange. Okay, so the estimated threshold for sideband generation is P equals 4, M and W, which matches the experimental observation. The power per generated comb line ranges from microwatts up to several milliwatts, significantly higher than the current state-of-the-art down-converted mid-infrared combs. So the keyword is mid-infrared optical frequency combs at 2.5 based on a crystalline microresonance. I'll continue in the next video. So actually I'm going to put keyword tags from data. So we'll just say a little mini formula here. We had effective, retractive index, NEF, silica, vapor, water, and hydrophobic crystals. I think that's it. Okay. I'll just date that. And I'll put that in on the notes when I do the video. Or when I upload it. And during filming. So I know what happened. Retractive, refractive. Oh, it's supposed to be refractive. There we go. Enough. Okay. Okay, so that's good. Okay, thanks for watching. We'll go on to the next video now.